Data Encryption Standard or DES algorithm. It is a symmetric block cipher. This is a very important topic in the field of security and computing because this acts as a basis for all the symmetric block encryption algorithms. And this was very widely used till the end of 1990s. Even though towards the end of 1990s, it was attacked through some cryptanalysis methods. But still, DS is supposed to be a basic algorithm to teach the working of a symmetric block ciphers. This is fundamental algorithm for all the modern symmetric block ciphers. So let's see a brief history about the DS. IBM initially developed something called a Lucifer cipher by a team led by Feastel in late 60s. They used 64-bit data blocks with 120-bit key. Later, a commercial version of the same was developed from the inputs from NSC and others. And in 1973, the National Bureau of Standards issued a request for proposal for a national cipher standard. They needed a national cipher standard, and based on that, the IBM submitted a revised Lucifer, and which is then accepted as the Data Encryption Standard or DES. Coming to the steps in DES, initially the input is divided into 64-bit blocks. The input plain text is converted into 64-bit blocks. Then it is permuted by, what is permutation is, then it is permuted by a so-called initial permutation. As in the case of SDS, it is permuted by a so-called initial permutation. Then we do a set of cycles, that is in rounds. We do data processing in sequence of cycles, where in each cycle or in each round, the data bits are transformed by a 64-bit key. So in each round, the data bits are transformed by 64-bit key. Why it is written as 56 also? Because as soon as the subkey generation algorithm gets the 64-bit key, it just removes every 8th bit. That is, in a 64-bit, you have in total, you have around 8 bytes. LSB of every byte. LSB of every byte, assuming that is a parity bit, LSB bit of every byte is just deleted. So the 64-bit key is truncated to a 56-bit key. Since this is open, we know that even though you are giving a 56-bit to the system, as soon as it receives it, it will delete every 8th bit and makes it a 56-bit key. So in many of the text, it is given as DS is using a 56-bit key. Actually, the key is 64. So we can say either it is a 64-bit key or a 56-bit key, no problem for that. So in each round, the data is transformed by a 56-bit key. And this cycle or this round is repeated 16 times. And then after that, a last cycle, after the last cycle, after the last cycle, a final permutation, which is inverse of the initial permutation, is performed. A final permutation is performed after the last cycle, which creates what we call the ciphertext. This is shown in the form of a diagram here. So this gives the general structure of the DS. The 64-bit plain text is performed an initial permutation. Then we start with the round. In each round, we apply a function to the data using a key, a subkey K1 that is provided by a subkey generation algorithm. So to the subkey generation algorithm, we give the input as a 56-bit key. From the 56-bit key, it provides the necessary subkeys for each round, using which we apply the data transformation each round, and this is repeated 16 times. So rounds are repeated 16 times, so which means the subkey generation algorithm has to provide 16 subkeys. And after the 16th round, we perform a final permutation, which is nothing but the inverse of the initial permutation. And you know what inverse is? The same thing that was there in SDS. It performs an inverse of the initial permutation, which we called as final permutation, and the output of that becomes what we call a 64-bit ciphertext. So the input to the system is 64-bit plain text and a 56-bit key, and after encryption, it creates a 64-bit plain text. Now, this is the overall architecture of the system. So input is taken, input is of size 64 bits. Then it performs an initial permutation. Initial permutation. Then it actually divides the 64-bit block. That is, after the initial permutation, it divides the 64-bit block into two halves called left and right halves, L0 and R0, each of size 32 bits each. So after the initial permutation, the 64-bit block is divided into two halves, each of size 32 bits. Now, inside each round, it performs a processing on the right-hand side to the right half, a copy of the right half to a copy of the right half. It performs a data transformation using a subkey provided by the subkey generation algorithm. Then it exclusive OR with the actual left half, producing the new right half. And the previous right half is going to be the new left half. Okay, so this is performed in each round. In each round, we will see in detail later. So after initial permutation, you divide the two halves, we enter each cycle, and the cycle is repeated 16 times. And the output that you get from the 16th round, we merge it together and we perform an inverse. When you merge it together, we again get a 64-bit block. We perform a final permutation, which is nothing but inverse of the initial permutation that we performed, inverse of the initial permutation, or we call as the final permutation, is performed here, and thereby we get the 64-bit ciphertext. So before going to the round, let's see what happens during the initial permutation. So in initial permutation, what happens is, so the initial permutation, you know what a permutation is? An initial permutation is performed based on this table. So here we can see that bits 1 to 8. The bits 1 to 8 of the input goes to which bit positions of the corresponding output is given in this particular table. So bit number 1 goes to 40, bit number 4, position 40 of the output. Bit at position number 2, this is 1 to 8. Bit at position 2 of the input goes to 8th position of the output. Bit at position number 3 goes to 48 of the output, likewise. So the first 8 bits goes to these corresponding positions of the output. The next 8 bits will go to this corresponding position of output. So likewise, each bit is permuted. All the 64 bits are permuted using this table, and is called initial permutation. So this is performed during the initial permutation. And after the initial permutation, you again divide into two halves and enter the cycles. At the end of the cycles, again we perform a final permutation. So let's see what a final permutation is done. So final permutation is based on this table. So again, the first 8 bits of the input that is given to the corresponding output positions as per this table. And you know that final permutation is inverse of the initial permutation. Final permutation is inverse of the initial permutation. So understand that we can compare the two. So if you look at this table, we know that the two tables are combined. So as per this table, we said that bit at position number 1 went to 40 of the output for initial permutation. So bit at position number 1 went to 40 of the output during initial permutation. And this is table for final permutation. Let's see the bit number 40. So here, these are the bits for 33 to 40 given here. And you can see that the bit at position number 40 is coming to the first position of the output. So this is inverse. 1 went to 40 and 40 came back to 1. So you can look at this diagram. Bit at position number 1 went to output position 40 during the initial permutation. And after the 16th rounds of encryption, the bit at 40, after 16th rounds, the bit at position number 40 came back to position 1 of the output. So initial permutation is, final permutation is just the opposite of initial permutation. Again, if you look at bit number 2, as per this table, bit number 2 went to 8. So here, bit number 2 went to 8th output position during initial permutation, and bit at position 8 of the input came back to position 2 during the final permutation, which is inverse of the first one. So all the bits are just coming back to its original position. So final permutation is just the opposite of initial permutation. So these are the initial permit. This is supposed to be the architecture, and this is what happens during the initial and final permutations. Now let's see what happens during each cycle. So this gives more clarity about what happens inside each cycle. This is supposed to be the encryption process or data processing that happens in each round, and for that, how the subkey generation algorithm is going to give the subkeys for that round. That is depicted in this particular diagram. So first, we'll see the subkey generation algorithm. So assume that this is a particular round called Ki. This is a round Ki whose input are two 32 bits. Half, one is called left half and right half, each of size 32 bits, because we already divided, after the initial permutation, we divide the 64-bit block into two halves called left half and right half, each of size 32 bits. The same thing is given as input for every cycle. So let us generalize it. So for a cycle I, it gets the input as Li-1 and Ri-1. And I told you, like, each round needs a subkey called Ki. Each round needs a subkey called Ki. So before going to the round, let's see how the Ki is generated. Now, the key that you get, the 56-bit key, even though we are providing a 64-bit key, I told you, like, all the 8-bit is deleted, making it as a 56-bit key. Now, once the system gets a 56-bit key, the subkey generation algorithm will divide it into two halves. The key also, the 56-bit key, is divided into two halves called Ci and D, called Ci-1 and Di-, let me. Two half, each of size 28 bits. So the 56-bit key is divided into two half, each of size 28 bits. And each half is separately left shifted. Each half is separately left shifted. Left shift means left rotate. It is left shifted by certain bit positions. And how many bit positions has to be rotated left depends on a particular table. Let's see the table here. That depends on this particular table. If you are going to generate subkey for round number 1, the number of bits we need to shift is 1. That is, I need to shift 1 bit to the left if this key generation algorithm is for cycle 1. Like this subkey, this Ki is, the I is 1, which means I need to shift 1 bit position to the left. So if it is for round number 5, I need to shift left 2 bits to the left. So depending on the key, depending on the round in which you are present, based on this table, you need to left shift that many bits. That's the meaning. So depending on which round it is, based on as per that particular table, we need to perform a left shift. Both half we perform left shift and certain bits will be left rotated. Now after the left rotation, we combine it together. We combine the two half. After the left shift, we combine the two half and we give it as input to a permutation box or permutation choice box. So after the shift, after left shifting, both are separately left shifted. We combine it together and give it to a permutation choice box. We give it to a permutation choice box, and let's see what happens inside a permutation choice box. So this is the permutation choice box, and this is permutation choice or choice permutation. That is, it reduces its size. We know that the input is 56 bits. The 56 is divided into two half, and we left shifted, and when you combine it together again, it formed a 56-bit input. And when you give to a permutation choice, when you perform permutation choice as per this table, this is permutation choice, it neglects certain bits. So here, these are the input bits, and the corresponding output bits is given in this table. So bit at position number 1 goes to 5th position of the output. Bit at position 2 goes to 24th position of the output. Likewise, it will go. And bit at position number 9 is just neglected. It won't go to, it just deleted or just neglected. It won't go to any new location. So like this, you can find some dashes here. So many bits are deleted, around 8 bits, 1, 2, 3, 4, 5, 6, 7, 8. 8 bits are deleted, and all other bits are just permuted. So input was 56, out of that 8 bits got deleted. So output will contain just 48 bits. This is permutation choice. From the 56-bit input, we permuted, we apply permutation choice and get a 48-bit output. So after the permutation choice, we get a 48-bit output, and that is supposed to be the sub key for that particular round. So this is how we create the sub key. And you have to note here that after the left shift, after we perform the left shift, let me take pointer. After we perform the left shift, we combine it together and we are going to the permutation choice box. And a copy of the same is kept, and this is given as input for the subkey generation algorithm for the next round. So for I plus 1, for the round I plus 1 for the subkey generation algorithm, in the round I plus 1, this Ci and this Di is going to be the input. Again, they perform the left shift and all this stuff. And again, the number of bits is it has to left shift is based on that particular table. So now we generated one subkey called Ki for this round. Now let's see what happens inside the round. We are ready with the left half and the right half, and we are ready with the subkey required for that particular round. Now we'll go to what happens inside a round in DES encryption algorithm. Now, among the left and right half that is given as the input to the DES encryption algorithm, you take a copy of the right half, and we give to an expansion permutation. We perform an expansion permutation. So the input is 32-bit. A 32-bit input is given to an expansion permutation, and we get an output as a 48-bit. So we perform expansion permutation and get a 48 output. And so let's see how the permutation is performed. This is expansion permutation. You know what's the property of an expansion permutation. So expansion permutation is performed as per this table. So bit at position number 1 of the input, goes to two new positions of the output, like 2 and 48. So bit at position number 1 goes to bit position 2 and 48. Bit at position 2 goes to 3, 3 goes to 4, whereas 5 goes to 6 and 8. So copy is taken and go to 2 new positions. 8 goes to 11, 13. So certain bits will go to 2 new positions, certain others will go to some new positions. So this is expansion permutation. So after expansion permutation, the 32-bit input is permuted and expanded to a 48-bit block. Now we are here, we have a 48-bit block. This 48-bit block is exclusive or with the 48-bit key. Already the subkey generation algorithm gave a 48-bit subkey. So we just exclusive of these two. The output of the expansion permutation is exclusive or with the 48-bit subkey. Now the output of this 48, the output of the exclusive OR. So each of size 48 bits, and the exclusive output is again going to be a 48-bit output. This 48-bit block, is given to a substitution choice box, an S box that performs substitution choice. The 48-bit block is now, after the exclusive OR, it is given to a substitution choice called S box. Now let's see, this is substitution. So let's see how the substitution is performed. Okay. Yeah. So let's see with an example how the substitution. So here we know that for the substitution, we are having a 40-bit input to the substitution choice box or for the S box. So once it gets the 48 bits, it just divided it into 8 blocks. So we have a 48-bit block that is given to the S box. It is divided into 8 blocks of 6 bits each. So each is having 6 bits. Now let's see what happens to one of the blocks. Let's say we take the first block, S1. So S1 is taken first. S1 has 6 bits. Now just like SDS, S box in the SDS, we just take out the middle 4 bits and combine the first and last bit together. So we combine the last bit with the first, and the middle 4 bits is taken out separately, and these two values are given as inputs to an SBox table. So you know the similar thing that we had done in SDS algorithm. So similar to that, from the 6 bits that is there in S1, we combine the first and last bits, and the middle bits are separated. These will give a row and column of an SBox. So first and last bit will point to, since we have 2 bits here, the values range from 0 to 3. That is, select a row. In the middle, you have 4 bits. So 4 bits means the value ranges from 0 to 15. That selects one of the columns of the SBox. So as per our example, it was 101100. That was the value that was there in S1. So as per our example, it selects row 2, column 6. The value is 6. So as per our example, it selects column 6 and row 2, and the corresponding value is 2 here. So the value, so if you look at the entire row, you find that the value ranges from 0 and the maximum value is 15. Since the maximum value is 15, when you look at the entire values, if you not just that row, you just go through the entire values in the complete SBox, the maximum value you can find is 15. So to represent a value 15, you just need 4 bits. So the output from the SBox is represented in the form of 4 bits. So input was 101100. That was a 6-bit input. A 6-bit input was given to SBox 1, and we generate a 4-bit output from this SBox. So the same thing is repeated for the other 7 blocks of the same SBox for the same substitution choice box. So for a substitution box, we had a 48-bit input block that is divided into 8 blocks of 6 bits each, and then we apply it to a particular SBox, and we get 4 bits from that. And so we reduced the first 1 to 4 bit. The same thing is repeated for the remaining blocks of that particular SBox, and the difference is for each one. See, the 48 block is divided into 8 blocks. We saw how it is reduced for S1. But for S2, we do the same thing, but we use a different table that is given here. So this is the table for substitution box 1. This is a table for substitution box 2. Likewise, you have substitution table 3, 4, 5, 6, 7, 8. So we know that the input to a substitution box is 48 bits. As soon as we get a 48 bit, it is divided into 8 blocks. We call it as S1 to S8. And substitution is performed on the table just we saw. So for S1, we use a particular table. For S2, we take a different table. So for all the blocks S1 to S8, we use different tables, and each one will yield a block of size 4 bits. So when you combine it together, we get an output of 32, an output block of size 32 bits. So this is substitution. We are performing substitution as per that table. So the value is substituted. Okay. Going back to the round. So we are here. We performed the substitution choice. The input was 48 bit. That was substituted and reduced to 32 bit. Now this 32-bit block is now given to a permutation box, a normal permutation box P. So let's see what happens inside. This is normal permutation. You know, normal permutation means just moving to new positions. So we are giving to a normal permutation box P. Normal permutation is performed as per this table. This table that is used for the permutation box P. So 1 to 8 bits, the first byte of the input. So we have 32 bits in total. Among that, 32 bits means we have 4 bytes. The first bit, 1 to 8 bits, goes to the corresponding output position as per this table. The next 4 bits goes to the corresponding positions here. So bit number 9 goes to 24 of output. Bit number 10, bit at position number 10 will go to 16 of the output. Likewise, we perform the permutation here. So we perform the permutation. Since this is normal permutation, the output is of size again 32 bit. Now the 32 bit output you get from the permutation box. We perform an exclusive OR with our initial left half. So this is as per the principles provided by the Feastal cipher. We apply the function, this is the round function. We apply the round function to a copy of the right half, and then we substitute it with the left half. So for that, we perform an exclusive OR with the initial left half, and we generate the new right half. Okay. So this is how we perform the you can say the round data transformation in each round. So after applying the transformation or exclusive with left half, we generate the new right half. And the initial right half, we applied the function to a copy of the right half. The other copy is given as the new left half. So just inverted the left and right half. The previous left half is going to be the new right half, and the previous left half is substituted with a function applied to right half and a exclusive with it, and then we generate the new right half. So this is how the new left and right halves are taken, and these left and right halves are given as input to the next cycle. This is repeated 16 times, and at the end this is performed, or this is repeated 16 times, and at the end we combine it together. We perform an inverse initial permutation and generate something called the cipher text. So in DES encryption, we divide our plain text into 64-bit blocks, and we provide a 64-bit key, and we create ciphertext for size 64 bits, and we transmit to the other end. So this is how the encryption is performed. Now, decryption is also similar to encryption. We do the same thing in decryption. That is, we give a 64-bit ciphertext, a 64-bit block ciphertext as input. I'm talking about the decryption. In the case of decryption, we give 64-bit ciphertext as the input. We perform the same initial permutations, perform the same round. The difference is the subkey that we use is key 16. For encryption, we use the subkeys in the order K1 to K16. K1 to K16. But for decryption, we use K16 first. We use the last subkey first. That is for cycle number 1. We use the subkey K16. For cycle 2, we use the subkey K15. So the subkeys will be used in the vice versa, in the reverse order, and we perform the decryption in each round. And after the 16th round or 16th cycle, we combine the two halves of 32 bits each. We perform a final permutation, which is again inverse of the initial permutation. We perform the final permutation and we get the plain text back. So decryption is very much similar to encryption. The only difference is subkey is used in the opposite order. And to prove decryption is the opposite of encryption, we just need to prove, we need to check whether the output that you get from during each rounds of the encryption. This is again the each round of the encryption. In each round, what happens is Li-1 and Ri-1 are the inputs that is given to each round, and at the end of the round, we get the output as L of I and R of I. Now, if we want to check decryption during decryption, whether we'll get the cipher, we will get the plain text back. In order to check that, we need to verify whether using Li and Ri as the input to a round, whether we can get Li-1 and Ri-1. That is, in each round in decryption, we need to check whether we get Li-1 and Ri-1 from Li and Ri. So this is how it happens during decryption. So to prove that, what we do is, we know that in encryption, we know that L of j, that is L of j is, or L of I, here we take as L of j. So let's take it as j. L of j is equal to R of j minus 1. So L of j, because a copy of the right half is taken as the new left half. So the output of a half called as Li or L of j, whatever it is, L of j equal to R of j minus 1. That is straightforward. And R of j is nothing but L of j minus 1 exclusive or L of j minus 1 exclusive or a function of Ri minus 1 with key k, with the subkey k. That is, we apply a function f, we apply function f on the right half rj-1 with subkey ki. So if it is j, it is rj-1. We apply function f on the right half rj-1 and key kj, and exclusive or with the previous left half rj-1 that yield the new right half. So this happens during the encryption. So since this is mathematical formula, we can rewrite these equations as if L of j is equal to R j minus 1, then you can say that R j minus 1 is equal to L of j. And by the property of the exclusive OR, that is if A equal to B exclusive OR C, then you can write B equal to A exclusive of C. That is if Rj plus R of j exclusive OR this function of Rj minus Kj will yield Lj minus 1. So that is the property of an exclusive OR. Lj minus 1, we can write it as Lj minus 1 is equal to R of j exclusive OR f of Rj minus 1 comma Kj. Now we know that Rj minus 1 is L of j. So substituting this Rj minus 1 with L of j, we can rewrite it as Lj minus 1 is equal to R of j exclusive or f of Lj comma Kj. So from 3 and 5, equations 3 and 5, that is Rj minus 1 is equal to L of j. Rj minus 1. During decryption, this is going to be the output. So the output that you get during decryption each round is supposed to be the input of that particular round. So we can find in each round, we can prove that the inputs is related to the outputs of that particular round. So Rj minus 1, Rj minus 1, yeah, Rj minus 1 is equal to L of j, and Lj minus 1 is equal to R of j, the equation R of j plus f of Lj comma Kj, the inputs that is given to that particular round. So we can prove that the decryption, it is in each round, it is reversible. Each round in DS is reversible. You can get back Rj minus 1 and Lj minus 1 from L of j and R of j. This is a function applied on L of j and R of j. You can get L of j minus 1 and Rj minus 1 you can directly from L of j. So we can prove that decryption is just the opposite of encryption in the case of DES. And thereby you can get the plain text back. Now, avalanche effect. This is a common property with which we measure the strength of encryption algorithms. Avalanche effect says that it is a desired property of encryption algorithms. It says that for a small change in either the plain text, that is for a small change, 1 or 2 bits, for a small change in either the plain text or the key should produce a significant change in the ciphertext. That is for two plain text blocks that differs by just 1 or 2 bits using the same key should generate a total different ciphertext. That's called avalanche effect. That is 2 input blocks of 64 bits that changes by some bits, say 1 or 2 bits. For the same key, it produces a big difference in the ciphertext. Then we can say that it has a strong avalanche effect. So making attempts to home in by guessing keys is impossible. If it has the avalanche effect, it will not give any clue about the key. And DS exhibits a strong avalanche effect that is evident from this particular table. So if I change, say this is shown with two ciphertext that, two plain text that differs by 1 bit. What happens if I use two plain text that differs by 1 bit? After the first round, the ciphertext produced had difference of 6 bits. After round number 2, it differed by 21 bits, etc. After round 16, the two ciphertext generated had a difference of 34 bits. That is, for 2 input blocks that differ by just 1 bit, for the same key, we got 2 ciphertexts that differed by 34 bits. And when this is for a particular bit. And for another bit, that can be different, but this is an average. On an average, it is giving that much difference in the case of DS. 34 bit means in total we have 64 bits in each block. So more than 50% of the bits, changed during each encryption in the case of DS. Same thing happens for the key. If we change the, this is the same thing, the change in key. the change in key happened. Similarly, for two plain text with the for two similar plain text, for two similar plain text, that is for two same plain text blocks with 1 bit key for the 1 bit change for the key, that is for two same plain text with 1 bit change for the key. If you perform the encryptions, what you got is, after round number 1 we got 2 bits being changed, that is both the plain text were same, we just changed 1 bit in the key and you perform two different encryptions. And after round number 1, the output you got had 2 bits being changed. After round 2, we had 14 bits being changed. Like that, after 16th round, around 34-bit was different when you compare the two ciphertext. That is, DS is having a strong avalanche effect. The first case, we use the same key with two plain texts that differed by 1 bit. In the second case, we use two plain texts, entirely same plain text with two different keys that change in 1 bit. Two keys that has a difference in 1 bit and used for encryption, and we compared the ciphers generated, and the generated ciphertext had bits being changed in 35 positions. Bits in 35 positions were totally different in when you compare the ciphertext. So DS is having a strong avalanche effect. Coming to strength of DS, basically the strength of DS is defined in three aspects. One is key size. The DS is using a 56-bit key. Since it is using a 56-bit key, we have around 2 raised to 56 possible key combinations. So for a brute force attack, you need around you need to try with around 2 raised to 56 different combinations. So at the time, the brute force attack was not possible. We can say it was not possible, but later on with some modern computers and with parallel processing and hypercomputers coming to the scenario, we could break it, but still till 1990s it was said that it was totally betrayed all the your brute force attacks. The second one is the nature of the DS algorithm. The strength of the algorithm is dependent on its S boxes. So we know that before giving the input to the S boxes, we just exclude her with the key. The left half after performing the copy of the right half after performing expansion permutation, we exclude her with the key and give it to the S box. So if you don't know the key, we cannot have an assumption about the input that is going to give to the S box. So the S box is designed in such a way that if you don't have any clue about the inputs to the S box, you cannot get any clues about the output that you are getting from the S boxes. As long as you don't know the key, you cannot get any conclusions about based on the output. You will not get any conclusions about the input that is used for each S boxes. So the strength of this algorithm is basically lies in the strength of the design of its S boxes. And timing attack. Timing attack is a totally different attack that is performed in some encryption algorithms. That is, for certain encryption algorithms have a property like, for certain category of plain text, it takes different times. I mean, for certain category of plain text, it takes some, say, 10 seconds. For other plain text, it may take more time. So the time taken for encryption, for certain encryption algorithms, the time taken for encryption greatly depend on the format of the data that is given to the system. So by carefully looking at or by analyzing the time taken by the system for encryption, the cryptanalysis or the attackers can get some clue about the plain text or about the key. So that is the problem with some encryption algorithms during that time. But DS algorithm doesn't have that much problem. Whatever be the format of the input plain text that is given or the key that is selected, the DS encryption algorithm almost takes the same amount of time for encryption. So the time taken for the encryption does not depend on the pattern. It does not that much depend on the pattern that is used as the input plain text or the key. So DS is supposed to be fairly resistant against timing attacks. So these are the three aspects that provide strength, or we can say define what is the strength of our data encryption standard algorithm. Okay, so that's it about the DES encryption algorithm.